So today we're going to talk about calculating magnetic fields and forces. So what we learned in the lecture was that you can calculate the force on a moving charge or a current, which is also moving charges, in a magnetic field by using the equation force equals QVB times the sine of the angle between V and B, or the force equals ILB sine theta, where I is the current and L is the length of the wire. B, of course, is the magnetic field in Tesla. So since it goes as sine theta, if the current or the direction that the charge is moving is parallel to B, then the angle is 0 and the force will be 0, and the force will be a maximum where sine theta is 1, which is when the angle between them is 90 degrees. The direction we went over a lot last time using the right-hand rule shown above. So today we're just going to do calculations. We'll assume you understand how to do the directions. So the first two calculations are very simple. It's just using the two equations. Let's do one for the force of a current on a wire and one for the force on a charge. So the first one, we have a 1.8 meter long wire. So that's my L. 1.8 meters. Carries a current of 13 amps. So that's my I. At 35 degrees to a magnetic field, so 35 degrees, that's my theta, to a magnetic field of 1.50 Tesla. So that's my B. So just like you do for any problem, go through, pull out all the numbers, figure out what they are. So I've got I, L, B, and theta. So I'm trying to find the force. All I have to do is just directly plug in F equals ILB sine theta. The problem gave me all of them, so all I have to do is plug them in. So the current is 13 amps. The length is 1.8 meters. The field is 1.5 Tesla. And the angle is 35, so it's going to be sine of 35. If I plug all that in, I get a force of 20.1, and I should round that to two significant figures, so 2.0 times 10 to the 1, and the units for force are newtons. So pretty straightforward, just plug the numbers into the equation. All right, let's do one using the QVB equation. So here I've got a proton, so I know a proton has a charge of plus E. So it's going to be plus 1.6 times 10 to the minus 19 coulombs is Q. It's traveling at 23 degrees. 23 degrees, that's an angle, so there's my theta. To a magnetic field of 2.6 millitesla. So that tells me my B, and it's milli, so 2.6 times 10 to the minus 3 Tesla. And it feels a force of 6.5 times 10 to the minus 17 newtons. So that's my force, and I want to know what is V. All right, so if I look at the equation, F equals QVB sine theta, the problem gives me F, gives me Q, it gives me B, and it gives me theta, and it asks me to find V. So V is equal to F over QB sine theta, just divided by everything on the right hand side except for V. And so now I just put in my numbers. So F is 6.5 times 10 to the minus 17. And I'm going to divide by Q, 1.6 times 10 to the minus 19. Times B, 2.6 times 10 to the minus 3. And sine of 23 degrees. So when you put this into your calculator, make sure you're using lots of brackets in the denominator or you'll get this wrong. I get a speed that's quite large, 4.0 times 10 to the 5 meters per second. Okay, so those kind of calculations are pretty straightforward. Just do the goal method where you gather all the numbers out, organize it, figure out what you have and what you need, and then do the algebra. All right, so, excuse me. The next thing is to find the magnetic field due to a long straight wire. So the picture there again shows you what we talked about in the last lecture, which is what's the direction of the field due to a current. So the field goes around in a circle around the current. Put your thumb along the current, and your fingers of your right hand will curl in the direction that the field loops around. The size of the field B is mu0 over 2 pi, where mu0 is the permeability of free space, and it's equal to 4 pi times 10 to the minus 7. I is the current, and R is the distance that you are from the wire, and you're measuring the field. So remember when we calculated E, the electric field, we used the permittivity of free space, epsilon 0. For magnetic field, we use the permeability of free space. Okay, so first of all, let's just think about what happens if we have more than one wire. Well, if we've got more than one wire, we're going to have to add the fields as vectors, just like we did for electric fields. So if I think about, let me just do one of these examples here. So if I've got a current going into the field, into the screen at 1, I'm going to take my thumb, put it at 1, make sure it's the thumb of your right hand, and you'll find that the magnetic field from 1 goes around in a loop in a clockwise direction. Similarly for 2, it's going to loop around in a clockwise direction. For 3 and 4, put your thumb out of the screen because the current's coming out, and the magnetic field is going to go around counterclockwise for those. So if I extend those circles out so their diameter goes through the circle, you can see that B2, when it gets to the center, is going to be going in that direction. B3, if I extend this loop out, is also going to be going up towards the top diagonal. And similarly for 1 and 4, if I extend those circles for B to the center, you can see the direction that they're in. So if I added those 4 field vectors, what would I get? I would get something that's going to the left. And you can do something, I'll let you guys work out this example here. Again, put your thumb into the screen if it's the X, out if it's the dot. See which way your field goes. So let me do it for these ones. So it's going to go either clockwise or counterclockwise. Add those arrows together. If I add those arrows together, they all cancel each other out. So 3 cancels out 2, 1 cancels out 4, and you end up with 0 magnetic field. So this is sort of a concept you should be able to work out. All right, so let's do a calculation. So I've got 2 long straight parallel wires, 8 centimeters apart, and they have the same current. So I is the same for both of them. And we're told the magnetic field halfway between them is 300 microtesla. And so the first thing it says is, are the currents in the same direction or in opposite directions? And then what is the value of the current? All right, so first of all, let's draw a picture to make sure we understand what's going on. So we have 2 wires, and they've got 8 centimeters in between them. And let's straight away put that into meters, 0.08 meters, just so we're in the right units. And I'm told that halfway in between them, so halfway in between them, I'm at a distance of 4 centimeters from each wire. So R is 0.04 for both of them. I is the same, I don't know what it is. And I'm given that B is 300 microtesla. And this is the total magnetic field. So each of these wires is going to create a magnetic field. So let's just do some thinking about it. So let's call them wire 1, on the left, wire 2 on the right. So let's say I have the current in 1 is coming out of the screen. So imagine a long straight wire going through the screen. Current in 1 comes out of the screen. Take my right hand, put my thumb coming out of the screen. B1 is going to go in a circle that's going counterclockwise. So in the center, B1 is going to be going straight up towards the top of the screen. If wire 2 is also coming out of the screen, then B2 is also going to go in the counterclockwise direction. Then B2 at the center will be going down. So B1 and B2, they have to be the same because it's the same current and the same distance. They will cancel out. So if the current is in the same direction, then the B's subtract and B total is equal to 0. So since we know that B total is not 0, that means that the currents, the answer for A is that the currents are in opposite directions. If the currents were different or the distances were different, then we couldn't make this assumption. So it's the fact that the magnetic fields are the same because the currents and distances are the same that allows us to tell which direction it is. If the distances weren't the same, like it's going to be for your sample problem, then you would have to be told. So now let's assume they're in the opposite direction. So B2 goes in, so the I2 goes in. And so B2, put your thumb in, B2 goes around clockwise. So B2 is also going to go up towards the top of the screen. So that means that the total field is B1 plus B2. Okay, so I know my B total. What's B1? B1 is mu 0 I1, which is just I, over 2 pi R, and we know R. And B2 is mu 0 I over 2 pi R. So those are the same. So it's just going to be 2 times mu 0 I over 2 pi R. Okay, so let's see what we got. We can cancel out the 2's. All right, so B total is mu 0 I over pi R. What am I trying to find? I'm trying to find I. So I'm going to rearrange, bring everything else over to the other side. So I is going to be, take the stuff from the denominator, multiply it up. Pi times R times B total divided by mu 0. Okay, so pi times R, 0.04. B total is 300 micro, so times 10 to the minus 6 Tesla, divided by mu 0. Mu 0 is 4 pi times 10 to the minus 7. And so if I put that all into my calculator, I get a current of 30 amps. Okay, so in general, if you've got two wires that are running parallel to each other, if the currents are in the same direction, the field in between them will be subtracting. If they're in the opposite direction, the currents between them, so if the currents are in the opposite direction, the fields between them will add together. Okay, so the last thing is to talk about the force between two parallel wires. So if I've got two wires that have a current running in them, wire 1 is going to create a field B1. So if you look at the picture in figure B, if I've got a wire with a current going up towards the top of the screen, put your right hand with your thumb going towards the top of the screen, you can see that your fingers circulate in the direction shown by those sort of blue whirlpools. So at wire 2, it feels a field going into the screen. Okay, so now we're going to do our right-hand rule. Do your right-hand rule, so your fingers will point along I2, bend in the direction, bend into the screen. Okay, so point in the direction of the current up towards the top. Put your palm into the screen. What direction is the force? The force of 1 on 2 is towards wire 1. So wire 2 gets attracted towards it. Similarly, if I have a current in 2, that current in 2 makes a field at 1 that attracts wire 1 back over. So I can calculate the force by using force equals ILB. So the force on wire 2 is equal to the current in wire 2 times the field due to wire 1. And the field due to wire 1 is mu0 over 2 pi times the current in 1 divided by the distance between the two wires. So if I put that all in, I get the force on 2 due to 1 is mu0 over 2 pi I1 I2 over d times L2. And the force on 1 due to 2 is a symmetrical equation. It's mu0 I1 I2 over 2 pi d L1. So you can see the only difference between those two equations is the length of the wire. So usually what we do is we write this equation as force per unit length, and then you can see the force per unit length of wire 1 on wire 2 is the same. It's just the product of the currents divided by the distance between them times mu0 over 2 pi. So just like I was discussing on the previous page, parallel currents will attract each other, anti-parallel will repel. So I already showed you the example of why parallels attract. Let's do anti-parallel repel. So again, put your thumb along I1 going up towards the top of the screen, and you see that B1 goes in circles that way. Put your thumb in the direction of I2 towards the bottom of the screen, and you see that B2 goes in circles the opposite direction. Okay, so the direction of B1 at 2 is in. The direction of B2 at 1 is in. All right, so if you put your fingers in the direction of I1, so point your fingers going up towards the top of the screen, put your palm so that it's going into the screen in the direction of B2, you'll find that your thumb points in this direction. So wire 1 gets pushed away from wire 2. Okay, how about wire 2? Now you can put your fingers going towards the bottom of the screen with your, because that's the direction of I2, with your palm pointing into the screen, which is the direction of B1, and you find that the force on wire 2 due to wire 1 is away. Okay, so parallel currents attract, anti-parallel currents repel. So let me do a quick example here. So here I've got two wires, 25 centimeters apart. They carry parallel currents of 1.3 amps. What's the force per unit length on wire 1 due to wire 2? And what's the direction? So force per unit length is mu0 over 2 pi I1 I2 over 2 pi d. So I know the currents. They both are 1.3 amps. I know mu0. I know the distance between them is 25 centimeters or 0.25 meters. So all I have to do is put my numbers in there. So F over L is mu0, 4 pi times 10 to the minus 7 times the current squared over 2 pi times 0.25. And I get 1.35 times 10 to the minus 6 newtons. What's the direction of the force? Well, if you look at the picture, the currents are in the same direction, so they're going to repel. So the force on wire 1, parallel currents attract each other. So the force on wire 1 is towards wire 2. Force on wire 2 is towards wire 1. All right, so what do I want you to do? So the first thing I want you to do is, so assume you've got 2 wires, the blue wires there, 1 and 2, that are carrying current up towards the top of the screen. And I want you to find what's the magnetic field at that location there that's 1 meter away from wire 1 and 0.7 meters away from wire 2. So ignoring the fact that wire 3 is there, find the magnetic field at the location due to wire 2, and then add them together. So you got to figure out, are they in the same direction? Are they in the opposite direction? Do you add your answers from A and B, or do you subtract them? What's the net direction going to be? Should be either in or out. And then finally, in part D, calculate the force per unit length on wire 3 due to wire 1. So you want to calculate F31, and the force on 3 due to 2, F32, and then figure out, do you have to add them or subtract them to get the net force per unit length on them?